Are you preparing for any competitive exam in electronics field and you want to crack that exam in first attempt? Then this is a video for you. You have clicked just on the right icon because in this video we are going to learn one topic that is included in most of competitive exam syllabus like GATE and ILIT scientist job exam, DRDO exam, etc. That is none other than steady state error. So please stay with me. I'm Abhisha. Let's get started. System. Hope you all are familiar with this word. We use different types of systems in our daily life. Now, who can tell me a definition for this system? Alright, when a number of elements or components connected in a sequence to perform a specific function, that collection or group is known as a system. And when an input or excitation is applied into this system, it produces an output or response. Now, I will give you some examples of systems in our daily life. First one, an electric motor, where input is the electrical energy and output is the mechanical energy or rotation. The next one, air conditioner, where input is the electrical energy and output is changes in ambient temperature. Finally, a vehicle. It may be a car, bus or train. Here, acceleration or deceleration is the input and vehicle displacement is the output. Hope you got a clear picture of system. Let me now take you to next concept, control system. A control system is a system where output quantity is controlled by varying the input quantity. The systems used for controlling voltage, pressure, temperature are examples of control system. We can broadly classify control systems into open loop systems and closed loop systems. Let us first focus on what is an open loop system. A system which does not automatically correct the variation in its output, or a system in which the output quantity has no effect upon the input quantity, is known as an open loop system. This means that the output is not fed back to the input for correction. You can see a schematic diagram of open loop system here. R of t is the input applied and C of t represents the corresponding output produced. For example, an electric clothes dryer is an open loop system. Depending upon the amount of clothes or how wet they are, an operator would set a timer. And at the end of that, the dryer will automatically stop even if the clothes were still wet. So in this example, the clothes dryer would be an open loop system as it does not monitor or measure the condition of the output signal, which is the dryness of clothes. Then the accuracy of drying process or success of drying the clothes will depend upon the experience of operator. In fact, in an open loop system, the output can be varied by varying the input. But sometimes there may be changes in output due to external disturbances. And when there is an output change due to disturbances, it's not followed and corrected by this system. That's why we are moving to closed loop systems. This form of control system has one or more feedback loops. That means the output from the system will be measured and compared with the input in order to ensure that derived output matches with the desired response. Air conditioner is an example of closed loop system. It automatically adjusts its temperature depending on room temperature. You can see the block diagram of a closed loop system here. It consists of an error detector, controller, open loop system and feedback block. The reference input here corresponds to desired output. The feedback signal is proportional to output signal and it is applied into error detector. The signal produced by error detector is the difference between reference input and feedback signal. This error signal is modified by this controller and applied into system for correcting its output. That is the basic working of closed loop system. Moving on to time domain analysis of systems. The time response of a system can be decomposed into transient response and steady state response. Therefore, the total response y of t can be expressed as y of t is equal to yt of t plus yss of t, where y of t is the total response of the system, yt of t represents transient response, and yss of t represents steady state response. In control system, transient response is defined as the part of time response that goes to zero as time tends to infinity. On the other hand, the steady state response is simply the part of total response that remains after the transient has died out. Got it? I think it may be a little confusing. Don't worry, you will get a clear picture when we start our analysis. Switching focus to steady state error. It is defined as the difference or error between the output and reference input when steady state, that is t tends to infinity, is reached. You can see it's a response of a first order system. R into u of t represents reference signal and this is our output. At this point, that is when time becomes very large, you can see difference between reference input and output, and this difference is termed as steady state error. Got it? Let us now do some analysis of this steady state error. For that, consider a closed loop system. Here, R of s represents Laplace transform or frequency domain representation of reference input. E of s represents Laplace transform or frequency domain representation of error signal. C of s represents frequency domain representation of output signal. G of s open loop transfer function. H of s feedback transfer function. G of s H of s loop transfer function. Clear? Now start the analysis by writing the expression of E of s. From this diagram, it is clear that E of s can be expressed as R of s minus C of s into H of s. It is written here, E of s is equal to R of s minus C of s into H of s. Then this C of s can be equated to E of s into G of s. It is written here, C of s is equal to E of s into G of s. Now replace this E of s with R of s minus C of s into H of s. So we get E of s is equal to R of s minus E of s G of s into H of s. By rearranging this, we get E of s is equal to R of s by 1 plus G of s into H of s. Let E of t represents the error signal in time domain. So we can write E of t is equal to L inverse of E of s. That is L inverse of R of s by 1 plus G of s H of s. Then let ESS represent steady state error. As I told you earlier, steady state error is the value of error when steady state is reached. That is when t tends to infinity. So we can write ESS equal to limit t tends to infinity E of t. Hope you remember the final value theorem, that is, if f of s represents Laplace transform of f of t, then limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. Now we are going to use this theorem for finding out steady state error. Based on this theorem, we can write ESS that is equal to limit t tends to infinity E of t that is equal to limit s tends to 0 s into e of s. Then replace this e of s with the r of s by 1 plus g of s h of s. So we get steady state error ESS is equal to limit s tends to 0 s into r of s by 1 plus g of s h of s. Thus we obtained the expression of steady state error. Now we are going to find out steady state error of different types of systems for different types of inputs. So let's have a quick review on type number of control system. In fact, the number of poles of loop transfer function lying at origin is termed as type number of a system. Hope you remember g of s h of s is the loop transfer function, and it can be expressed as ratio of two polynomials in S, that is k into p of s by q of s, which can be expanded into k into s plus z1 into s plus z2 into s plus z3 etc. divided by s raised to n s plus p1 into s plus p2 into s plus p3 etc. where z1, z2, z3 are the zeros of transfer function, p1, p2, p3 are the poles of loop transfer function, k is a constant, and n is the number of poles at origin, which is our term of interest. Let us now find out steady state error of system with step function input. As you know, unit step signal can be mathematically expressed as r into u of t. It is graphically plotted here. You can see for t less than 0, its magnitude is 0, and for the time interval 0 to infinity, it is having a constant magnitude r. Since the input r of t is r into u of t, its Laplace transform r of s can be written as r by s. As I said to you earlier, the steady state error of a system ESS is equal to limit s tends to 0 s into r of s divided by 1 plus g of s h of s. Now what we are going to do is we are going to replace this r of s with r by s. So we get ESS is equal to limit s tends to 0 s into r by s divided by 1 plus g of s h of s. And it can be written as r by 1 plus limit s tends to 0 g of s h of s. Now let us represent this term limit s tends to 0 g of s h of s with kp. Correspondingly, our steady state error ESS becomes r by 1 plus kp, where kp is limit s tends to 0 g of s h of s, and it is known as positional error constant. Thus, we obtained the expression of steady state error when the input is unit step signal. Now, what we are going to do is we are going to consider different types of systems and find out corresponding steady state error for unit step input signal. Let us first consider type 0 system. As I said to you earlier, in type 0 system, the number of poles of loop transfer function lying at origin is 0. Hence, our loop transfer function g of s h of s becomes s plus z1 into s plus z2 into s plus z3 etc. divided by s plus p1 into s plus p2 into s plus p3. Correspondingly, kp can be equated to limit s tends to 0 k into s plus z1 into s plus z2 into s plus z3 etc. divided by s plus p1 into s plus p2 into s plus p3 etc. By applying limit s tends to 0, our kp becomes k into z1 into z2 into z3 etc. divided by p1 into p2 into p3 etc., which is a constant. Correspondingly, our steady state error, that is r by 1 plus kp, is also becomes a constant. This constant steady state error is shown here. You can see at this point the difference between the reference input and output is a constant. So we can conclude that the steady state error of type 0 system for unit step input signal is constant. Switching focus to type 1 system. Here the number of poles of loop transfer function lying at origin is 1. Correspondingly, loop transfer function becomes s plus z1 into s plus z2 into s plus z3 etc. divided by s into s plus p1 into s plus p2 into s plus p3 etc. And our positional constant kp can be written as limit s tends to 0 k into s plus z1 into s plus z2 into s plus z3 etc. divided by s into s plus p1 into s plus p2 into etc. By applying s tends to 0, we get kp is equal to infinity and correspondingly es is equal to 0. So we can conclude that the steady state error of type number 1 and above systems for unit step signal input is 0. Clear? Next we are going to consider a unit ramp signal. That is, we are going to do the analysis of steady state error for different types of system when a ramp signal is applied at its input. As you know, this is the waveform of a ramp signal and it can be mathematically expressed as r of t is equal to rt u of t. In fact, the detailed analysis of steady state error for unit step signal is already done. I think you can follow the same procedure and do the analysis for ramp signal. So here I will give you only the results. Please try to do the complete analysis yourself. If you get stuck at any point or if you have any doubts regarding this, please do let me know in the comment section. I will definitely help you. Let me now take you to the results of this analysis. When we apply a ramp signal to type 0 system, its steady state error will be infinity. And for type 1, it is a constant. For type 2 and above, it is 0. Hope it is clear. A constant steady state error for ramp signal is illustrated in this figure. This is our reference input and this is our output. At this region, you can see a constant difference between reference input and output or a constant steady state error. Alright, switching focus to next topic. Here we are going to do the analysis of steady state error for parabolic signal. As you know, this is the waveform of parabolic signal and it can be mathematically expressed as r of t is equal to rt square by 2 u of t. Here also I will be giving only the results of this analysis. Please try to do the complete analysis yourself. When we apply a parabolic signal to type 0 system, its steady state error will be infinity. And for type 1 it is infinity, type 2 it is a constant, and type 3 and above it will be 0. Clear? A constant steady state error for parabolic signal is illustrated in this figure. This is our reference input and this is output. At this region, the difference between reference input and output is a constant, or you can say that its steady state error is constant. Alright, that's all for today. Thanks for being with me. Hope you all enjoyed this lesson. See you soon. Bye.